Welcome, my dear students of PG semester 2nd Chemistry CC4 group to this class. Today we will study the rest some cases regarding entropy. In continuation of previous class, we will study the calculation of entropy. Calculation of entropy change of an ideal gas with change in pressure, volume and temperature. Pressure P, volume V and temperature T. Suppose dq amount of heat absorbed by an ideal gas. dq is a small amount. Amount of heat is absorbed by an ideal gas or which is a system reversibly from surroundings at temperature capital T. Then increase in entropy of the gas for an infinitesimally change is given by Bs equal to dq reversible by capital T. We know from the definition. But from the first law of thermodynamics, first law of thermodynamics, we know dq reversible equal to du plus pdv, where du is the change in internal energy here. Change means increase. du is equal to increasing internal energy dv is equal to a small change in a small increase in volume of the gas.
One minute.
P is external pressure, and PdV is work done. You may say work of expansion. In this equation, dividing both sides by t, write down, dividing both sides by t, we get dq reversible by t is equal to du plus pdv divided by p. This may be equal to dq reversible by t equal to du by t plus pdv by t. Clear? But we know du by t is equal to Cv, a specific heat of gas at constant volume. We know Cv is equal to du by t a specific heat of gas at constant volume. Therefore, d is equal to CV into T. CV is equal to du by dt. CV is equal to du by dt. So therefore, du is equal to CV dt. CV dt. This is for 1 mole of gas. For 1 mole of gas, we know PV is equal to RT. Gas equation for n mole of gas is PV is equal to nRT. So if we put n is equal to 1 for 1 mole of gas, the PV is equal to RT. So therefore, we may write P is equal to RT divided by V. Putting these value du and P in this equation, we get dq reversible. Suppose this equation is 1. I write down from equation 1 we get equation 1 is dq reversible by T is equal to du by T. So du is equal to CV dt. CV dt plus P dV by T. P is equal to RT by V. RT by V into dV by T. Now this T and T is cancelled here. We may write now we know dq reversible by T is equal to ds, a small change in entropy, ds from the definition of entropy, and this is CV dt by T. CV, we may write this d ln P, d ln T plus R dV by V equal to d ln V. We know integration of dV by V is equal to ln V. From this formula, we can write d ln V, which is opposite to integration, d ln V. So this is entropy change, a small entropy change. For infinitesimally a small change, this equation is ds is equal to CV d ln T plus R into d ln v. For total chain, we integrate this equation. On integration, I am going to total chain in entropy. Integration ds equal to integration of Cv d ln t plus Rd ln v. Here R is a gas constant and Cv is also a constant. So on integration, we may write integration of ds equal to s is equal to Cv integration of d ln t plus R integration of d ln v. That is S equal to Cv and d ln t integration of d ln t is equal to ln t. Cv ln t plus R integration of d ln v is ln v. R into ln v and some constant. Suppose this constant is I1. I1 is integration constant. Equation 3. I1 is integration constant. Now, for an ideal gas, we know Cp minus Cv equal to R. So therefore, Cp minus R is equal to Cv. Or we may say Cv is equal to Cp minus R. Putting this value in this equation, we may write thus above equation becomes S equal to Cp minus R into ln T plus R ln V plus I1. It will take some time. from this equation S equal to CPLNT minus RLNP plus RLNV plus I. This will be cancelled. Oh, RLNT, no, RLNT, CPLNT minus RLNT plus RLN or some point is missing. CPLNT, RLNT, RLNV. Oh, in this equation, since we know PV is equal to RT, so V is equal to RT by P. Put this value also. CPLNT minus RLNT plus RLN RT by P plus I1 this is equal to CPLNT minus RLNT plus, and this becomes RLN RT minus LNP plus I1. This is equal to CP LNT minus RLNT plus R, and this is LNR plus LNT minus LNP plus I1. CPLNT minus RLNT plus RLNR plus RLNT minus RLNP plus I1. This minus RLNT and plus RLNT is cancelled here, and this RLNR is a constant. By adding from this constant we get another constant. We may write thus CPLNT minus RLNT plus RLNR plus I1. This is another constant. Therefore, S equal to CPLNT minus RLNP plus, say, RLNR plus I1 equal to I2. say R ln R plus I1 equal to I2 is another constant. Value of I1 and I2 cannot be obtained from thermal capacity, but the change in entropy delta S can be determined. Now we may write down values of I1 and I2 cannot be obtained from thermal capacity but the change in entropy can be determined. By taking two cases, initial case and final case. Consider case first. When T and V are the two variables, T and V are the two variables, temperature and volume. If the temperature of the gas changes, if the temperature of the gas changes from T1 to T2, and due to which volume from V1 to V2 from above equation we may write entropy in this case S1 is equal to CV ln T1 plus R ln V1 plus integration constant I1 and in case second from above equation S2 will be equal to CVln T2 plus RLn V2 plus I1. Therefore, change in entropy delta S will be equal to entropy in second case minus entropy in first case. S2 minus S1 will be equal to, we will get by subtracting this equation from this equation, CV ln T2 minus ln T1 plus R ln V2 minus ln V1, and this I1 will be cancelled, minus this will be cancelled. After subtracting from this equation to this, we will get delta S, that is change in entropy. Delta S change in entropy is equal to this CV ln T2 minus ln T1 R ln V2 minus V1. Therefore, delta S will be equal to CV ln T2 minus ln T1 is equal to ln T2 by T1 plus R ln V2 by V1. This is entropy change for 1 mole of gas. This is the expression for, you may write, this is expression for entropy change for 1 mole of a gas. If you take n mole of gas, if you take n mole, since entropy is an extensive property, so entropy will be multiplied by n, entropy change. For n moles of an ideal gas, entropy change will be n times of this delta Sn, n for n mole, delta S for entropy change. Delta Sn is equal to, here this will be multiplied by n, so n into Cv ln T2 by T1 plus nR ln V2 by V1. In this case, temperature and volume are variables. Another case, here we must write for when T and V are variables. Take another case. When temperature and pressure are variables. When temperature and pressure are variables, following similar procedure for one mole of gas we may write delta S CPLN in place of CPLN T2 by T1 minus R ln in place of V. Here comes pressure P2 by P1. Similarly, for n moles of gas, this equation comes by putting into a say P1 V1 by P2 V2. We know for 1 mole of gas, therefore we may write V1 by V2 is equal to P2 by P1. By putting value of V1 by V2, or we may write minus V2 by V1 equal to P2 by P1. So here minus sign comes, and in place of CV we put CP. No, CP. Sorry. Value is CV. CV ln T2 by T1 minus R ln P2 by P1. Is obtained from the temperature volume expression by replacing V2 by V1. For n moles of gas, similarly we have delta Sn is equal to n CV ln T2 by T1 minus n into r ln P2 by P1. These equations are expression for change in entropy of an ideal gas with change in pressure and temperatures for 1 mole change, and this is for n mole change. Now considering the change of a state in different processes, consider change of a state in different processes. Such as isothermal process, isobaric process, isochoric process, etc. First case, if the change be an isothermal, in isothermal process temperature is constant. In this case T1 will be equal to T2. Suppose this is equal to T. Therefore T2 by T1 will be equal to T by T equal to 1. Therefore from above equation we may write for 1 mole of gas change in entropy isothermal for isothermal sign at constant temperature, this will be equal to R ln V2 by V1 minus this will be equal to minus R ln P2 by P1. Or this may be written as R ln, it will be reversed, P1 by P2. Since ln T2 by T1 is equal to ln 1 and this is equal to 0, so the term ln T2 by T1 becomes 0 in both the equations. This is equation when volume is variable. This equation when pressure is variable. Second cat for B for isobaric process. In isobaric process the pressure is constant. For isobaric process P1 is equal to P2 is equal to P से Therefore, ln P2 by P1 equal to ln P by P equal to ln 1 equal to 0. So, we may write change in entropy at constant pressure by putting ln P2 by P1 equal to 0 in the above derived equation. We get delta Sp equal to Cp ln T2 by T1. Now come to the third case C for isochoric process. In this case, volume is constant. That's V1 is equal to V2 is equal to V6. The above equation reduced to delta SV, change in entropy at constant volume, will be equal to Cv ln T2 by T1. And last case, now we will study in the next class change in entropy of mixing of two ideal gases, and after that we will study free energy, gives free energy, etc. Thank you very much.